All right, welcome back to CS 194. This is lecture 8, and I'm going to be talking today about a little bit more about OpenMP and about synchronization primitives in particular, and you'll be learning and using this more in lab this week. So just to start though, I want to review a little bit or give you kind of what I'll call the money picture. What good is this roofline model? I guess I didn't show you, and part of it is we haven't studied all these different algorithms, but this is what it looks like when you take a bunch of different types of computations with different computational intensity and put them on a roofline plot. And this is actually on two different processors, on an Intel Nehalem, which is a traditional, although somewhat older now, multi-core processor, and then also on a GPU. And so they have different bandwidths and they have different peak gigaflop rates that you can see here on the roofline. DGEM is dense matrix matrix multiply. We'll use that. I think I mentioned that before. This is some other computations. I think I mentioned last time a 7-point stencil computation, which is this yellow one. You can see it sits, when it's well optimized, it sits very close to the memory bandwidth peak. Sparse matrix vector multiply, well, it's a little bit different than dense matrix vector multiply. We'll talk about that a little bit later, but it is also sitting, in the sparse case, you have a little bit more memory overhead, so a little bit less computation, lower computational intensity, even than dense matrix multiply, but both of those will sit right on this memory bandwidth peak. There's a few different dots here because there's different types of matrices of the sparsity structure that will give you slightly different computational intensity, and also are either easier or harder to optimize for various reasons in terms of the memory system. Things like prefetching and things like that will be different. But anyway, this gives you some picture, hopefully, of the power of the roofline model is that we can tell all of these codes are quite well optimized. Actually, there's a lot of graduate student time and postdoc and staff time at the time this work was done that was put into optimizing these, and they get close to the roof line, and you know that these sparse matrix, these matrix vector multiply things are never going to run at anywhere close to the peak of dense matrix matrix multiply. This is double precision matrix matrix multiply because it just doesn't have the computational intensity. Just wanted to cover that. Now I'm going to switch back and talk about OpenMP. We wanted to give you a little bit more of this performance stuff, the performance modeling and the roofline model. I'm happy to answer any questions about it if you have any, but otherwise I'll go on and talk about a little bit more about OpenMP and specifically about some of the things that come up with synchronization. But we'll work through an example here, but just to remind you, and I know you've seen this both in 61C and also you were working with it in lab last week. It has this fork join style parallelism. So it's got a main thread here, and that main thread continues in a parallel region as one of these threads, and that the parallelism can be added incrementally to the program by typically it's mostly done by adding parallelism to loops. There are other places you can put parallelism, but in most OpenMP parallelism, if you're going to get any substantial amount of parallelism, it's because you've parallelized one of the loops. You can also nest the parallelism. So this little example on the right shows that there's parallelism inside of this parallel region, and that's also possible in OpenMP. Okay, and there's just some of the loop constructs and some of the primitives. I think you used, well, certainly the OpenMP parallel. And I haven't talked in lecture, although I think you've seen some of this in lab, the different ways in which you can execute parallel loops. But we also have the ability to ask for how many threads there are, to set the number of threads, and to ask what thread number a particular thread is in a particular piece of code. So the example that I'm going to use here is estimating the value of pi, and it's going to be using this formula, which is that pi is equal to the integral of under the area under this piece of the curve from 0 up to 1. And if you need to, you may go back and review a little bit of your trigonometry and stuff to see what this is, and I guess a little bit of calculus, although really we're just looking at these chunks and adding them up, and to see that this will turn into, we'll be able to use this to compute pi. So we're going to approximate this by the sum of these rectangles, right? The exact value of pi would be the area under this curve but we can't compute that numerically. And so but we can get a close approximation by using narrower and narrower intervals, which will get closer to this curve. And so we're going to write a little program to do that. Here's a serial program, so no parallelism at this point. And the serial program is just computing these. It takes in the number of steps, so, or at least it's a constant here. And so we're going to have a step size, which is equal to 1 over the number of steps. We've got some variables we're going to accumulate into the sum so far of the areas that we're computing there, and a value for pi and a value for x, which is just looking at that plot, what the value is of x is as we're going through it. So a particular point on the x-axis, and then the height of that, which will be used to compute the area of the rectangle. And so we go up to the number of steps, and we increment by the step size in each case, and we compute this sum. And then at the end, we have to multiply the sum times the step size to get the actual value of pi. Okay, so the stages that we're going to think about, we need to identify the concurrency. We need to think about how to expose that to some kind of tasks or some kind of parallelism in whatever language that you're working with, in this case, OpenMP. How to express that and make sure that it's safe to execute it in a parallel way. And then we're going to execute it and look at the performance and go back and tune and probably modify the parallelism, which we'll even do in this lecture. So the main computation, of course, in this program is this loop. And so we're going to look at looping. We can, in general, take a loop and we can execute it in parallel. So we can try to do this with this loop. Now we've got some problems in this loop because we've got some variables that are being updated in the middle of that, and that creates loop carried dependencies, or these are read after write hazards, if you will, because actually I guess there may also be write after read, but there's certainly read after write, which in one iteration of this loop, we're going to be writing the sum, and then we're later going to be reading it as we do the plus equals. So that we've got all these hazards on both of these variables. So is it safe? No, it's not safe for parallel execution. So we can try to parallelize it, but we're going to have to do something to make those variables work correctly. So we can, we're going to treat the two different variables in a somewhat different way. So the x variable, it turns out, we don't really need to, we're not really sharing versions of that across the different threads, or we don't need to. What we can do is just calculate x directly by the loop index. And now the loop index itself is changing, but that's going to be handled when we turn this into a parallel loop. And so then rather than having a plus equals of x and step, we'll just compute x as a function of I and these other variables that are constants, so 0.5, and then step, which is constant in the loop body. And then we're going to do something different with sum, which is we're going to think of this as a reduction. And so we're going to have to worry about how to deal with that a little bit later, but this one is still going to have this expression with the plus equals in it. And what we've done also is to separate then the variables. I've just written them in different places. The variables that are going to be shared, such as step isn't going to change throughout. And then the variables that we want to be local to a particular thread. So I is the loop index, which, as I said, as we parallelize this loop, each thread is going to have a different set of indices, and that means also a different set of variables. And because of the way we've computed x now, each of the tasks can have different values of x, and that won't cause any problems. Okay, so here's one way of parallelizing this loop. This might not actually be the most obvious way to do it, and in fact, maybe later we'll see something a little bit more natural, but this is going to be one way of doing it where we're going to fix the number, the expected number of threads, the max thread count. We'll just use a hash define here, in order to get a value. So we'll set the number of threads to be 4. And now we're doing something that we're going to make different copies of the variable sum so that they can all be updated independently in the loop, but we'll put them in an array, and this is sometimes called privatizing the variables, or by turning them into an array in which each thread has its own copy. And so they'll independently be updating the value of one of the locations of the sum index. So one of the array elements of the sum array. Okay, so I now also am going to use this ID to figure out what thread ID I have, and use that to index into this array. So I'll need to I need to compute that value somehow. And let's see. So I've now parallelized this, and this style of parallelism is really called single program or SPMD parallelism, SPMD parallelism. And we'll see this a lot throughout the semester, where what you're really doing is taking this chunk of code and having every processor, every thread that is, execute its own copy of that chunk of code. Now they're executing it independently, by which I mean it's not as though each one of these statements in there is happening at exactly the same instant, the same clock cycle on each one of the cores, if each thread is running on a different core, but it is going to be but they may happen sort of at any given point in time. So exactly, for example, the cost of a cache miss on one processor may cause it to run a little bit slower than one of the other cores, one of the other threads, so these are executing it kind of at their own pace through this, but roughly at the same time. And this OpenMP pragma now will create this fixed number of threads that I've defined with a macro. Okay, so now we've got this SPMD version of the code, this SPMD version of the program. They're all working on different pieces of data, so that's the multiple data part, but there's just one copy of the program. Okay, so let's see, go forward. Let's see. And so the variables now are declared inside this loop. And the private variables, remember we separated the shared ones like step from the private ones, and the private ones are declared inside the loop. Those are going to be private to any thread, and the shared variables are declared up here before the parallel loop, and those will be shared by all the threads. So all the threads can see the same value of step, and they're going to have different values. They can have independent values of int and ID and and x. And so that just is how we're separating the variables. Now there's a bug in this program, and does anybody happen to know what it is without cheating and looking at the slides? Okay, well, the bug in the program is that OpenMP, although we've asked it to give us a certain number of threads, technically the operating system may decide to give you fewer threads. And so to write this in a safer way, what you actually do is you ask OpenMP for the number of threads, and then we're going to use that to set. We're going to use that variable rather than using the nums constant that we've set here. So we're asking it for nums threads still, so for 4 threads. But in case the operating system gives us, and it's guaranteed not to give us more threads than we ask for, but it could give us fewer threads than we ask for. And so we fix this by using this variable instead, n threads, and then n threads is what we'll iterate up to in our loop that's jumping over jumping over each of the, jumping by the number of threads, so that each thread is going to get a different set of index i's in there. And the question is, wouldn't it be a better practice to use OpenMP parallel 4? And yes, and we will look at that. There's a particular reason we're writing it this way, because, well, is it better practice? It's better, it's certainly stylistically better to use an OpenMP parallel 4, and that would sort of clean some of this up. I wanted to just clarify this one point. But the SPMD style of using this fixed number of threads is something that you want to have in the back of your mind, even if you're using a parallel 4, that you want to make sure you've got chunks of work for each one of them to do and not just individual pieces of work. Okay, so we run this program, and not only is it maybe not written in the most elegant style, but it's also doesn't perform very well. So this is the serial. I'm calling this the serial sum version of the program because if you just look back at this, not only is this SPMD code, but here at the bottom of the loop, this is outside of the OpenMP region. I'm adding up all of the values of sum, looking at each of the values of sum to compute pi. And so this code is running serially after the parallel region of the loop. And so you can think back at that original picture where we have those, those groups of threads that are being created. And so those are being created in here. There's just one of those parallel regions, but this is happening afterwards in the serial region. Okay, so why is this performance so poor? Anybody want to hazard a guess as the reason? Well, the reason is false sharing, which I mentioned last time in passing, but I wanted to just give you a clearer picture of what this might look like. And also somebody asked last time a little bit about hyperthreads and which on that you can have multiple threads on a single core. And so why do you have that? To kind of remind you, hopefully from 61C, you might have that because there's some expensive resources on there, such as the floating point units. And you might want to share those floating point units, but you might want to have multiple threads that are actually look like they're executing independently, but whenever they get to, say, a floating point instruction, they'll have to take turns using the floating point unit or some other piece of hardware. And so in particular, some of the memory units and things like that are going to be expensive. So, so we can have two threads running on one core, and that's what the picture that we have here. And those might share, those would share the cache lines all the way up to the level 1 cache. But now if we have two cores, they probably will not share level 1 caches. And if you have, for example, two sockets, we talked about that last time, if you had two sockets, they may not even share level 2 caches and even level 3 caches, depending on the number of caches and what their purpose is and things like that. And so, but in this case, we have a shared cache, which is great in some ways, because that means that the hardware doesn't have to worry as much about consistency of those different cache lines, right? Because there's only there's a sort of one instance of it, except that in order to maintain that consistency, it has to make sure that if some thread on this that has this copy of the cache line is updating one of the values, and this other thread is updating another value, that cache line is going to have to move back and forth between those two cores. And so that sloshing back and forth of the cache line creates false sharing. It doesn't create the wrong answer, right? So it's not a race condition in the program, but it does create poor performance. And so when we privatized these scalar variables into an array, that gave us parallelism. It avoided the race condition that we had on the sum variable, but it created this other problem of false sharing. So the solution to this, and I won't show the code, but is to allocate bigger chunks in the array, or perhaps even maybe rearrange the elements in the array so that they're contiguous, and then pad it so that you make sure that each one of the cores will get its own, that you won't have a cache line boundary in between the regions that two cores are using. And you saw that kind of thing when we worried about cache structure, even in cache blocking on a single core. So now we can also use, rather than just putting the code in a separate part of the software that is not in the parallel region, sometimes that's not a very convenient thing to do. And so sometimes you want to have some protected part of the region that's going to run serially, even though it's in the middle of a parallel block. And that can be done with a critical region. And so in this case, it is still at the bottom here, but it's at the bottom of this for loop, and this critical region means that only one thread at a time can be executing this particular statement because it's protected by this critical clause. So we can also use that in order to implement our pi example. So this is really the same as it was before, except that we've now taken that extra separate loop out and put the pragma up here inside of the parallel loop region, but then protected it with a critical region. And so, so how does this one work look in terms of performance? So it actually is quite a bit better, and this has really gotten rid of the false sharing, I think, is the main reason that we get so much better performance in this case. But we've now also implemented that rather than by a separate serial part of the code by putting a critical region around it. And so those are the running times now for the two different versions, and I've just plotted this. By the way, I always like when I'm doing a speed up plot to include something which is the ideal speed up line, because that sometimes it can be hard, especially if you're doing, one of the axes is a log scale or something like that. It can be a little bit hard to tell what the ideal speed up is. And so it's useful to just show that on here. So we're getting, pretty close to ideal speed up on this code now. And but we can try writing another way and just to see how that will go. And in order to do that, we're going to look at some other types of synchronization constructs. So far you've seen a critical region in the code, and you see just running it serially, which is what we did originally, but we can also use various kinds of synchronization primitives, such as locks or barriers or atomic operations. I won't really talk about ordered operations today, but but it's another thing that is supported in OpenMP. So let's look at a barrier construct. So barriers are going to come up a lot in other programming models that we'll look at, such as message passing later. It's a very useful construct, but very heavyweight. So a barrier is going to be a point in the program that all the threads have to reach before any of them can proceed. So this is different than the critical region that we had before, because different threads could go into that critical region and come out of it independently if they were running ahead of the other threads. But in this case, you're going to really wait. If one thread is running slowly, all of the threads are going to sit here and wait at this OpenMP barrier. And so this is going to be different than the critical region, but can prevent us from having things being, for example, read and written at the same time, where we've got some dependence before and after the barrier statement. So we can also use an atomic statement in OpenMP, and that is going to be a little lighter weight again than the barrier construct. And the atomic statement says that a particular statement is going to execute atomically. And so here's another version of just a simple program that is doing a whole bunch of work, but wants to then update this one shared variable x atomically by computing this. And this is a very common programming pattern that you're going to see a lot when you've got something that you need to update by all of the shared by a number of different threads. A lot of times what you do is you update a local copy of it, and then you update the shared copy inside of either a critical region, or in this case using an atomic operation. This atomic operation, and you may remember this from 61C, may be something that executes a little faster on the hardware. Or not. It depends a little bit on how the compiler generates code for this, but there are going to be some built-in atomic operations that can run quickly, and there'll be other ways in which the compiler could generate code for this. For example, just putting a lock around this, which we'll look at in a minute, that may actually make it run slowly. So so that's what an atomic does. It says that this statement is indivisible, that threads can come up to this point at any sort of pace that they want, but when they get here, that one statement is going to be executed as if there is a critical region around that particular statement. Now we can also use locks, and locks have to be created and they should be destroyed. So this is in C++, we need to manage our memory. So there's an OpenMP init lock that will create a lock. It'll allocate a lock, and it puts the value into this pointer, and the OpenMP destroy then will free up the thing that's pointed to by this lock variable. The then set and release it using the OpenMP set and the OpenMP unset. And there's something, and this is important for performance, that you can use to test a lock. So does anybody know why you might want to test a lock independently of, say, unsetting it? So it turns out that it's actually much more expensive to set and unset a lock because that has to happen atomically in the hardware. So down at the hardware level, it's got to make sure nothing is happening that is simultaneously that two threads are trying to set or unset locks, or in particular set locks at the same time. You've also got to make sure the unset happens correctly. But a test is something that you may be able to do by just a simple memory read. And you've got to make sure that depending on exactly how the hardware implements that. So the test can sometimes be a faster thing to do. Now we've got to the hardware has to be a little bit careful about that. You want to be looking at a relatively up-to-date version of the lock. But you can't use this test to then figure out that you can go and access some shared variable, but you can use it to figure out that maybe it's now a good time to go ahead and lock the variable because it was currently unlocked. So those are the primitives for using locks. And here's a little bit of a kind of a sketch of a program that's going to it's looking at some array of a big bunch of stuff, and it wants to swap the two of the elements in that array, which might have a whole bunch of different fields in it, a whole bunch of different computations. So it's not something that you can do really easily. So there's a fair amount of work in here. And so what we're going to actually do is have a lock for every element of the array. So what this loop up here at the top is doing is creating an array of locks. So first of all, I've declared them of type OpenMP lock T. So this is the declaration. It hasn't created them or initialized them. Why do we do that with a malloc-like statement? I mean, which is really what this OpenMP init lock is doing. Is because those locks need to be shared so that if one thread locks them, the other thread can lock them too. So they somehow need to be sitting in the shared part of the address space, so in the heap region, not sitting on the stack. So that's why we separately, we can declare the type, the array of types, which are going to be pointers really, or you can think of them as pointers to that. It hides in the interface exactly what the data structure is, but then you initialize the locks. And they are things that are shareable then by all of the threads. You then go through and this is now a better style here. We're using OpenMP parallel, and we've explicitly then declared some of the variables, if we want to, as being private, which is another way of sort of sticking them down into the OpenMP region. And then we've got and here we're using them, so they inside of here we're computing a random location. So what are we going to do in this program? We've got a particular, for every element of the array, which is index j, we're going to compute some other random index, which we're doing by this call to random, which is going to give us an index I other, and then we're going to swap the stuff that are at those two locations at index I and index j, or I other and j, in the array of stuff. So now what I'm going to do is I need to lock both of them, right? Because I'm going to be reading from both of them and writing to both of them. So I'm going to do a set lock on both j and on the location I other. I'll do the swap stuff, and I will unlock both I other, and then unlock ij. And so statistically, if we've got a big, huge array, these are not going to interfere with one another very often. This program, assuming that it's doing a fair amount of work in this swap step and doing a bunch of computation, for example, in there, is going to be able to execute this, even if it's doing a fair amount of computation in here, as long as they're really at different, mostly at different indices, we're going to get have few collisions in here, and should not have too many problems with this. So, but does anybody see a problem with this particular program? In the way, right, and so the answer is yes, that this program can deadlock because you're acquiring two locks. Anytime that you're acquiring more than one lock at a time, you need to think about deadlock, because the problem is that one of the threads can be going through, and it's, for example, it owns, according to this outermost parallel loop here, this for loop, it owns, say, the index 3, and it locks that. And then another thread maybe is executing even at index 4. So an independent position, it locks its own location 4, and that's fine. But that second one might be then trying to acquire a lock on 3, and the first one's going to be trying to acquire a lock on could be trying to acquire a lock on 4 if they both happen to collide in terms of computing the other index as the random number that they're getting up here. And so although most of the time this program might work without having a deadlock, it can have this problem that they're both trying to acquire the lock. And these are blocking operations. That is, this operation, these lock operations will sit there and wait until the lock is acquired. So if both of them are trying to do an acquire of a lock that's already being held by the other, there's no way for that deadlock to get resolved. And so what you need to make sure you do in a program where if you need to have well, you can think of these as really nested loops here, nested locks here, because one is happening after the other. We acquire the first one, then we acquire the second one. You need to make sure there's a strict order to them so that you don't end up with this deadlock situation. That is, everyone has to acquire locks in the same order. So for example, you could, after you've computed this random number, you could figure out which one is larger, that is my index j or the index I other, and make sure that you always acquire the smaller one first. And although they may both then try to lock the same element, whichever one gets it is going to be able to lock the second one. Okay, so now the other thing we have to worry about a little bit when we start writing these shared memory programs, and this gets into kind of lower level details, and we will talk about memory consistency in more detail next week, but just to be aware of the way OpenMP handles this, you do need to worry about, in some cases, the values that are sitting inside of, say, the caches, but even more kind of obviously, we know that the compiler, when you turn on optimizations like -03, is going to reorder some of the statements in your program. And and what this flush command does in OpenMP is going to tell us that the values that are sitting in those registers, for example, need to be flushed back to memory to make sure that other processors can see a consistent version of that memory operation. So in this little program here where we've got two threads, thread 1 is executing x equals 1 and then y equals 1. Thread 2 is reading y and then reading x in the opposite order. And by the way, memory consistency problems, a trick is to always look for a figure-8 style pattern that will cause problems if something gets delayed. So there's no problem in this program with having thread 1, the compiler, move the x equals 1 to the y after the y equals 1, because there's no dependence between x or y. And similarly, there's no problem in thread 2. In fact, they're both reads of these variables for the read of x to happen before the read of y. And so if the program actually does that, then you can see something that would be an illegal value in terms of the memory consistency model, what's called sequential consistency, and we'll talk about it later, but it basically means that every thread, that the whole program should execute as if each thread executes in serial order. So if it executes in serial order, then if we've got x equals 1 followed by y equals 1, you should not be able to see y equals 1 and not see x equals 1. So thread 2 should not be able to see a 1 and a 0 then coming out of this, because assuming both x and y started initially as 0. Okay, and you've got homework assignments on these kinds of questions as well. But the point of this OpenMP flush is to make sure, for example, that the compiler doesn't leave something in a register when some other thread could possibly be accessing it. And so you can execute this OpenMP flush, which will push the value of, make sure the value of A goes back to memory. And flush and flush commands happen automatically. So for the most part, you won't need to worry about them if you're doing all of your synchronization with built-in OpenMP synchronization primitives like starting parallel regions. Everything will be flushed back to memory at those points. And the explicit barriers, which we've already talked about. So the implicit barriers happen, for example, at the end of these parallel regions. Entry and exit of critical regions also will flush the variables out of that processor that's going into a critical region. And whenever a lock or is set or unset, using the OpenMP lock commands. But if you start programming synchronization, like you try to use just a shared variable for certain synchronization, which you can sometimes do in particular programs, then you might need to worry about inserting flush operations to make sure, for example, if you just write a program that is sitting and spinning, waiting for a variable X to be set to 1, and some other thread is setting that variable, it starts out as 0, and some other thread sets that to 1, you need to make sure that that variable is getting flushed out to memory when you write it to 1, and similarly that a little while loop that's sitting there waiting for that to be 1 is going to have a flush to make sure it's actually getting the variable from memory and not just sitting in a register. And so this flush command is what is OpenMP's way of making sure that you can write those kinds of programs correctly. Now, the last thing we'll look at here is really a reduction operation. And a reduction operation is going to be used, and we talked about this back, I don't know, a few lectures ago, about this. A lot of times we want to do an operation. The example we've seen here and the example we'll see in many cases is a plus. And that plus operation is associative, at least modulo floating point arithmetic round off errors, which we oftentimes will not worry about in terms of if we're careful. And I should say that carefully because I'm married to a numerical analyst. So you have to know what you're doing, but oftentimes in the programs that we're looking at, we'll get an answer that's close enough, even if we add things up, floating point numbers up in a slightly different order. And if we're adding up integers, the order doesn't matter. And so it's definitely safe when we're doing it on integers. And that's one of the reasons, by the way, the floating point issue is one of the reasons that OpenMP and many other languages will make you sort of say something that about the fact that it's safe to do this operation as a reduction, and the compiler won't automatically do that for you. Although if you get a sufficiently high level of optimizations turned on, the compiler may actually also try to automate that, as we saw in vectorization. So a reduction takes in an operation, and it takes in, so for example, down here, it's taking in plus as the operator, and it takes in a variable that, or a list of variables on which that operator can be used in a reduction way. That is that the operators can be, their order can be changed using associativity. And so here is, in this case, we're saying that the average variable can be updated using a reduction operation. So inside we can use this, for example, inside a parallel or other kind of work sharing construct in OpenMP. And a local copy of each list variable is made then by the compiler, and it's initialized, which is depending on what the op value is, and we'll look at what these different initializations values are. So that's the other thing you have to have for your operators, an initial value. So for plus, it's 0. So we can initialize it to 0. And then the updates occur on the local copy, and the local copies then are reduced at the end into a single value. So you don't have to write the code that does this, which in some sense we wrote in the earlier versions of the Pi example, that we'd written it out as a SPIMD program, right, where each one of them is kind of just doing a chunk of work completely independently, and at the end, each of the, say, 4 threads just adds their 4 values together, or one thread adds those 4 values together, or in a critical region, each of them contributes their value to the sum. But OpenMP makes it much easier to write this, and that goes back to the earlier question about, isn't there a better way to write this program using a parallel 4? And this is what the reduction operation is doing. But just more generally then, these reduction operations and their initial values are, we can do it on a plus and the initial value is 0. We can do it on a minus and the initial value is, and on multiply and the initial value is 1. If you do it on a minus, then it's really turning each one of those operations into a plus using associativity on it, and then on a negative value, min and max, for example. And And then there's, you can also do it on ands and ors, so logical operations. And those, by the way, if you're programming another language like Fortran, which also has OpenMP extensions, the syntax would look somewhat different, but there's the C and C++ versions of those operators, what you can put in the OpenMP reduction construct. Okay, so what does our example now of pi look like using the reduction operation and on a sum? Well, here's what the code now turns into. And so it looks much cleaner, and we just are using this, well, we're still using the OpenMP parallel up here as opposed to the for, but we've just got this single loop and we're doing the reduction on the sum operation there. And remember, we already had a separate way of calculating x to make sure that we don't have any loop carried dependence. So the only loop carried dependence in this case is sum, which is then we've protected that in a certain way, or specified to OpenMP that it's okay to have that race condition, what would otherwise be a race condition on sum, by doing a reduction on it using the plus operator. Okay, and here's the performance of this code. It's actually not as fast as the one that we wrote before that had the separate loop doing the sum operators. That's probably because the compiler isn't quite as good at generating that code. What it needs to do with this code to make it run as fast is not only make sure that this thing happen, make a local copy of it, but make sure it sort of gets split out into a separate loop and things like that. And maybe it's or maybe there's some false sharing or something like that in the way it generates the code, although it hopefully shouldn't be doing that if it's got separate sum variables that it's accumulating into. So, but there's our version of the loop with the reduction and the running times and the speed up that we get. So, as with that you saw on a lot of the cache optimization work and a lot of the other the register blocking, and anytime you're interacting with the compiler, the actual performance you get out of it may not be exactly the performance that you were expecting to get based on what you think the compiler should be doing. But you may therefore need to try other versions of the code, such as a version that that separates out the sum explicitly and then has a critical region for it. Okay, any questions about those different versions? Code. Right. All right. Well, so OpenMP really allows this incremental way of parallelizing the code. It allows you to just look a loop at a time. And so what you're doing at every step when you're taking a serial program, it may be a big, a huge serial application, and trying to parallelize it for shared memory using OpenMP. And this was the motivation behind OpenMP, and it really came from the scientific community that wanted to be able to parallelize applications that were big, million lines of code or whatever, hundreds of thousands of lines of code at least. And so what they could do is just a little bit at a time go and express the concurrency in it by looking at a particular loop nest in the program or a particular loop, and then looking at how you can turn that loop into a piece of concurrent code, and then just add the OpenMP directives, maybe do some other optimizations, such as putting in a reduction or privatizing variables or various other things that we've done in this example, but or switching between different kinds of synchronization using barrier synchronization if you need to, explicitly between, because you say merge some loops together, but you want a barrier between them, or using locks and things like that, and or atomic operations. And you do need to remember, as you're doing this incrementally, Amdahl's law, but as you go all of these transformations, you can try to make sure that you're getting the same answer of the program, that is you're preserving the behavior of each one of the transformations. So what do I mean by remembering Amdahl's law? If you start out with that big serial execution and then you add some parallel chunks to it at various points in time, the only pieces, right, of the overall running time that you're going to be getting speedups on are the pieces in those parallel regions. And so you can use Amdahl's law based on even the serial execution before you figure out which things to parallelize, what the estimated maximum speedup could be if you've got a certain number of cores or hardware threads on your processor that will allow you to get better performance out of those hardware, out of the parallelism. So you can use Amdahl's law to estimate that parallelism before you go to the work of parallelizing. And of course, a separate core you might expect to get mostly close to linear speedup out of, modulo if you've got locks in there, if you've got atomics in there, if you've got false sharing in there, something like that. Each one of those loops, if they're actually parallel, might give you close to the number of cores speed up. For hyperthreading, for multiple threads on a single core, you can also get speed up, but I wouldn't expect generally to get linear speed up a factor of 2. It really depends on whether the hardware resources that those hyperthreads share are the ones that are limiting the performance in the serial program, or if it's really separate pieces of hardware that each one of those hyperthreads has, such as its own registers, and it can do that computation on registers, and it then can maybe can get closer to linear speed up on the number of hardware hyperthreads. But typically we're going to use that more to use those to do things like mask memory latency and so on. So I call this both the strength and the weakness, this incremental parallelism model of OpenMP. What do I mean by that? And this is, by the way, not something I think Tim Hetson would say. I think he thinks that this is he's one of the developers of OpenMP, has worked on it for many, many years, along with a committee of others. You can find the OpenMP Consortium, which is a group online that is in charge of the OpenMP standard. And it's got a lot of hardware vendors in it, which have different competing interests in terms of how well their hardware will perform on a particular OpenMP construct. But what I really mean by this is that this incremental way of looking at parallelizing your program will often miss the fact that there is a better way to think about the problem in parallel, which will avoid these strings of serial performance in your overall runtime in your parallel code. And that Amdahl's law is something that is going to be sort of aided and abetted by incremental parallelism. That is, I think about my program as a serial program and I just parallelize little pieces of it, is very different than saying, let me step back and think about, could I solve this in a completely different parallel way? I could still write that program in OpenMP, but I might do it by, for example, in my main function, starting a fixed number of threads that's equal to the amount of hardware that I expect to run on, and then worrying about how to make that whole thing parallel. And that's a much harder program to write. So this incremental way, I can try to kind of get there by taking that incrementally built parallel version and then trying to sort of smush together the parallel regions by getting rid of the serial code between them, figuring out how to parallelize that, hopefully not by sticking locks or critical regions around it, because then that doesn't really fix the problem. But anyway, so those are, I think, just some things to think about in OpenMP as you're working on it in your homework assignments and your labs, and any questions about OpenMP or anything else for that matter. Okay, great. Well, thanks very much, and I will see you on Monday.